this one works. Okay, so we heard a nice resume of the previous day, which basically already gave us a nice introduction. So we return to Piero here. And, yesterday we saw he showed us how dynamical systems start working in a certain way, but then the question obviously is kind of natural, la domanda nasce spontanea, as they will say in Italy. How do you control these systems? How do you make sure that these systems do what you want them to do? Can you, say, drive a trajectory of a dynamical system to a certain point? Can you maybe pin it in a certain other state, and so on and so forth? And I suspect that's exactly what he's going to talk about now. And I'll be here with microphones in case someone has questions. As usual, just interrupt any moment, raise your hands, and I will pop behind you with the microphone. And depending if the question is good or not, and no, I'm not going to do that. Even though once I had a lightning session of lightning talks, and there was someone who was speaking for more than 5 minutes, and I actually started advancing with that. Have you ever seen a morning star? Also known as mazza ferrata in Italian and Latin. No, it was in Dresden, I'm not joking. Anyway, so let's talk about this later, or better even not, if there is no need to, and give the word to Piero.
Thank you, Sharon, thank you. So good morning again. I hope you had you enjoyed the first day, and I hope you will enjoy also the coming days. And so what we will discuss. So yesterday so Stefano made a lecture on synchronization. So when you study synchronization, you want to understand the condition under which this collective behavior emerges and all the trajectories converge all together. Now in control, you may not be happy just with that. You would like that this common trajectory is the one that you want the system to converge to. Okay, so that's the main idea. But just one question before we start. How many of you had a course in control theory? Okay, not so many. That's what I suspected. And so I will start with a brief introduction on what control is, because otherwise we might get lost. So this is where we will start with this brief introduction, in particular on the fundamental concept of feedback control. And then I will explain you what is one of the most popular strategies to control network systems on pairwise interaction, and then we will see how we can extend this strategy when we need to cope with higher order interaction, and why are higher order interaction important in control problems. Okay. And then we will see that the tool that was introduced yesterday by Stefano, the master stability function, can also be used in the case of directed network, as he already pointed out in the very last part of the talk. So when there was the question from Roberto. So let's start with an introduction on feedback control. So in general, the type what we typically call a closed dynamical system is okay, it's a bit unstable. Yeah. So in general, dynamical system, just from the standard definition, is a particle or ensemble of particles whose state varies over time and obeys to differential equations that involves time derivative. Okay, that's the classical definition. Yeah, we should somehow stabilize it. Yeah. Yeah, I think it works like this. Yeah. Yeah. So the classical, so you have x dot, you have a state variable x dot, then it is equal to a given vector field f, which is a function of time and of the state itself. Okay, so this is called closed in the sense that it is not affected by external inputs. Instead, what we call an open dynamical systems, we have the vector field that depends also on a third set of variables which are called the input variables that typically are denoted with the letter U. Okay, and then in addition you also have something which is related to what you can measure of the system, which is called the output. So the output is related to the state and possibly to the, in general, also to the input of the system through a static function h. Okay, so this tells you basically what you can measure of this system. Then, what's the main purpose of control? So the two main purposes of control are stabilization and tracking. So stabilization, you need to design the control input U so that the state will be stabilized around an equilibrium point. So the stupidest example, you have a refrigerator, you want the temperature of the refrigerator to be 4 degrees Celsius inside. And so this is a control system that stabilizes the temperature at this equilibrium point. Or you can have problems that are called tracking problems, in which you need to the system output to follow a given desired trajectory. So not an equilibrium, but a trajectory. Okay, not an equilibrium point. So this is the case, for instance, of control of, if you are controlling an aircraft, that's one possibility. You are controlling the dynamics of a car. And the type of control system, the two main type of control system that you can have are feed-forward and feedback control systems. So in feed-forward control systems, basically you know what is your reference trajectory, and based on the reference trajectory, you decide the control input to give to the system so that this trajectory is followed. In the feedback control, instead, you do something a little bit more refined, if you want. So what you do is you measure the output of the system, you compare it with the reference, you compute the difference between the two. The difference will be the error that you are committing in your control design, and so you're using this error to decide what is the control input that you have to give to the system to put this error to 0 so that the output will follow the desired trajectory. Okay? So now, let's make an example of so feed-forward control is called, well, for obvious reasons, you can see graphically. So feed-forward control is called open loop, and instead feedback control there is a loop which closes. It's called closed loop control. So you have this feedback action, and so you call it closed loop. In open loop control, so feed-forward, let's make an example. So if the system dynamics are linear, so the state is the derivative of the states are a linear function of the states and of the input, and the output also is a linear function of the state and the input, then you can design the control action in such a way that at steady state, so when you put the derivative to 0, you compute the steady state. At steady state, you will have that the steady state trajectory will be exactly the same as the desired one. Okay, so how do you do that? Well, you choose your variable. You have to choose KFF in such a way y infinity, so the steady state trajectory, is equal to the reference trajectory. So basically it has to be simply the inverse of this matrix product. If you make this choice, then at steady state you will have convergence onto the trajectory, onto the reference trajectory. Now, if you take a damped harmonic oscillator, yeah.
But this is the case in which the control is simply a constant sign.
Yes, yes. This is this.
More complicated functions.
Of course, so we are now we are making the simplest possible example. So we are keeping it as simple as possible. Of course, this u can be any function of yd, so it doesn't have to be a linear function. But let's make it simple, so the system is linear. We can manage it with a linear controller. But in general, the controller might be nonlinear. So in the example of a damped harmonic oscillator, basically, if you apply what we have just learned for general linear system, you will see that your feed-forward action you can design it to compensate precisely the restoring force of the spring, and so this is it. So you can do it. So all good, but not so good in the sense that the feed-forward action is not robust with respect to the presence of perturbations. So if there are perturbations acting on the system, yeah, unfortunately, yes. Yeah, unfortunately, I need to touch the computer to go to the next page. So this is a nice perturbation. So, yeah. So anyway, so if there is a perturbation acting on the system, then what happens is that a steady state, you will see that you will have that the steady state output will be equal to the reference output plus d over k, where k is the constant of the spring. Okay, so this means that with your controller, with your control action u, which is simply this kff times yd, you cannot reduce attenuate the effect of the disturbance. So you cannot mitigate the effect of disturbance. Why is that? Well, because basically you are doing your design based on what is the expected behavior of the system. Then the system undergoes some disturbances that you cannot predict a priori, and so you cannot compensate for that because you are just based on your model of the system and your reference signal. This is different when you consider instead a feedback action. When you consider a feedback action, basically, when you measure the output, you have within the output that you are measuring, it's contained the effect of the disturbance. We can switch to another one. Yeah. So while you continue setting up, so the idea is that when you have the disturbance acting on the system, so you will when you measure the output, in the output there is implicitly contained the information of the disturbance because the output is affected by the disturbance. So when you measure it and compare it with the reference signal, then you are actually taking into account when designing the control action of the disturbance, because in the error depends on the disturbance and is acting on the system. And so the simplest, again, let's keep it simple, but we will see that this simple approach, we will use it also for network systems. So a simple example is that of the so-called proportional control, in which your control action will be minus a gain, a control gain, so a constant, Kp, where P stands for proportional, times the error. So you have a proportional control action proportional to the error. And so basically, what happens? Well, it happens that when the error is positive, so let's assume that everything is scalar for simplicity. So when the error is positive, it means that your output is higher than the desired one, and so your control action will be negative. In the other way around, when your error will be negative, it means that your output is smaller than the desired one, and so you will have a positive input. Okay, so that's a very simple idea, very simple but very effective, because when you do your control design, so again, you check what happens at steady state when using a proportional controller. So now you can see, just you set all the derivatives to 0, compute the steady state, and what you see here is that you have the steady state, the control gain Kp is also affecting not only the steady state, it affects the steady state value and is able also to attenuate the effect of D. So here you can see that if you take Kp sufficiently larger than K, Well, the first term approaches YD, and the second term approaches 0. Okay, so you are able, by increasing the control gain, to attenuate the disturbance. Of course, yes, please. Yeah, so Kp times minus Kp E will represent the force that you will apply. Yeah. So the input in this case is the force that you apply to the mass. Okay. So with this choice, you are able to attenuate the disturbance. So this is robust to the presence of disturbances. Of course, you are not limited to using one or the other. You can also mix the two. So you can take the advantages of both schemes. So feed-forward typically gives you a faster regulation, while feedback gives you is able to guarantee properties of stability, robustness to uncertainty, and rejections of disturbances. Okay, and so what you do in control theory, you set a list of requirements that you wish that the system fulfills. So some of them you already mentioned: stability, robustness, the ability to reject disturbances. And then you need to find, of course, a way to enforce such requirements. How do you design the control action in general? How do you design it? Well, for linear systems, everything is simple in the sense that it is simpler. It's not so trivial, but everything is simpler because you can translate all these requirements into requirements on the position of the eigenvalues of the closed loop system. So when you design your function, you will find a new dynamical matrix for the system, which will be modified by the control action. And so depending on the eigenvalues of this new dynamical matrix, you can check if these requirements are fulfilled. When you have instead nonlinear systems, you need to resort to other techniques. So one possibility is the linearization, but also you have intrinsically nonlinear methods such as Lyapunov methods or passivity, or you have contraction theory. There are several options. Now, in traditional control theory, the focus was on a single system or a single device. So you want to control the motor, or you want to design the automatic pilot of an aircraft, or you want to design just the controller for the temperature of the refrigerator. So the focus was on the single system. Now, in modern control theory, instead, the focus is shifted onto the control of complex interacting systems. So spanning from power grids to neuronal systems to application in opinion dynamics, flocking, robotic flocking. So there are several transportation systems. So you have a wide range of applications. And so now the challenge is how to use the tools of control theory when you are not controlling one single system, like the damped harmonic oscillator, but you are controlling an ensemble of interacting systems. Okay? And so, as I mentioned, this is particularly relevant when you want, with reference to emerging collective behavior, such as synchronization and consensus that we talked about yesterday. And because when you don't want that the convergence is onto any solution or any fixed point of the system, but you want to enforce one specific solution, one specific fixed point, so you need to find a suitable control strategy to do that. So now let's discuss some example in which you want to design a control action. Let's make two examples which are very diverse from each other, and I would like to show you that even though they are very different, they share some common points. So one example is interbank financial networks. So whenever you go to a shop, you buy something by credit card, there is a financial transaction from your bank to the bank of the owner of the shop, right? So then you can build a network out of these, so where the nodes are the banks and the edges are the financial transaction, are the flows of money between the banks, basically. Now, what is the control problem here? So what is the control goal? And what is what is the input that we can give? So the control goal is to steer the market away from instability. What does it mean? We don't want liquidity crisis, right? So we don't want that some bank, and in particular, we don't want that some critical bank, which has a critical position in the network, as a liquidity crisis, because otherwise this can propagate in the entire network. Then you go to the ATM and you cannot collect money. So this is something that you don't want to happen. So what is the control input here? The control input here is, I don't know, central banks can decide to inject liquidity in the bank systems. But can they inject liquidity anywhere? The amount of money is not infinite. You need to decide how to distribute liquidity. Okay, so you need to find the critical nodes where to inject this liquidity. Maybe these nodes have some centrality property, so they are particularly relevant. They have some measure of importance that is particularly high. So you need to decide that. So where do I inject? So I don't inject everywhere. I need to identify the critical nodes. Now let's make another example. So in gene regulatory networks, they regulate the expression of proteins in cells and in our body in general. So one possible control goal is the inhibition of the growth of aberrant cells, which are typical. Yes, please.
I don't know anything of financial stuff,
Yeah.
you know, but just to understand, okay, the interbank financial network, isn't it an all-to-all network? Isn't it an all-to-all network?
It's well, it's
Yeah, sure, of course.
yeah, it can be quite dense. Yeah, actually.
Yeah, because I
But of course the weight of the
weight,
links
yeah.
is much different. Yeah.
Okay.
So this makes one node very different from
Different
the
from
other.
the- okay.
Yeah, because of that. Yeah, that's. So I was mentioning, so here the control goal in this type of networks is the inhibition of the growth of aberrant cells. So what is your control input? Your control input are drugs, of course, but drugs cannot act anywhere, so they can act only on accessible proteins. But also, you don't want them to act anywhere. You don't want that they disrupt the functioning part of the body. Okay, so these two examples are very diverse, but what do they have in common? That that our control action needs to be exerted only on a fraction of the network node. So not everywhere in the network, but in a fraction of the network nodes. Okay, and this is precisely the idea behind this control strategy, which is called pinning control. So in pinning control, the idea is that you directly control only a small subset of nodes, and with these few links, you would like to be able to drive the entire network to a desired behavior. Okay. So now yeah, sure.
Here we are actually positively using the network. Because if I don't have a network and I want to control each and every system alone without any interaction, it's obvious that I have to put a control everywhere. But if I have a network, so these units are interacting, I can put control only in some specific node and let the network propagate this control also to the nodes where I'm not active.
Yeah.
That's the point, you know. So it's a way that pinning control that the network system allows. If you have independent systems, it's obvious that you have to pin one by one. Because if it's independent and you don't pin, you will never control this specific node. Okay? So the pinning control is possible right because you have a network. Sorry.
Yeah, no, it's perfect. It fits perfectly because then you need to decide. Yeah, please.
So this means that the control theory is important when we don't know how each node is acting inside of the network, because yesterday we were talking about nodes where we know how the differential equations work inside of them. And here, for example, in the interbank system, we don't know how each of the banks work internally, how the customers are going to
Let's
transfer money.
let's assume that you know everything.
Okay.
But still, if you know everything and you don't control the network will evolve spontaneously by itself. So you will observe a certain behavior in the network. Now, this behavior you may like it, so probably you don't need to control the network if you like it. I will tell more about this statement in a second. But then, if you don't like the behavior of the network, you in any case, even if you know perfectly how the network works, you need to inject some control signal to make the network behave as you wish. Because even if you know perfectly how the interbank network works, and you can model it accurately, still you can have liquidity crisis anyway. But you don't want that. And also, even if the network is behaving properly, without a control action, maybe at some point it might behave in a way that you don't like. So still, the idea of having some control input that is activated when something happens or under certain conditions is always, yeah, please.
May I add something, just to clarify something, like a comment about this? In reality, if you think about it, you never know exactly what's going on anywhere.
Yeah.
Like, even in systems, like in situations models like opinion dynamics, we sometimes do. So like, with my opinion, I influence your opinion. With your opinion, you influence mine. In reality, it's not my opinion that influences yours and vice versa, because you cannot know what's in my head. And I cannot know what's in your head, so you can only judge by observing the actions of people.
That's
so
right.
in the same way here, you can only kind of infer what's inside dynamics of the nodes by observing some observable on the network.
So in the opinion dynamics, for instance, you have some kind of models which are you have continuous opinions. They are called continuous opinion and discrete action. So you have these continuous opinions, but then the action are discrete, and actually the action are the only thing that you observe. So you, yeah.
There was another question there, and I make another comment. That's also why, normally as a physicist, we prefer closed-loop control or feedback.
Yeah.
Why? Because in feedback control, as he said, you have these disturbances.
Yeah.
And now you can imagine that disturbances are not some external noise, but are the imperfect knowledge that you have on your system. So you measure your system. This is you measured. So for physicists, a measure is a measure. No? Galileo says there is the truth, the measure, the experiment. And this is something that enters the control loop because you are taking that. You have your goal, which is your goal, is subjective, the measure. And then you can say, okay, I don't know anything. I make an hypothetic model. And I consider the variation with respect to this as a disturbance.
That's right.
And then with the feedback control, I'm able also, to mitigate disturbances. So in a sense, the feedback control for a physicist is very important because even though you don't know perfectly the model equations of each unit, which is always the case, the feedback control is a good, nice operating way, so to say, to work. There was another question over there.
Yeah, in the back.
In the back, Estevao.
Wait for the microphone.
Hello. In theory, you are free to create new ping in your network freely.
You are free to create.
It's on.
Okay. In theory, are you free to create new pins in your network freely?
No, depends. You might have constraints. So you might not be able, some nodes may not be accessible. So you might not be able to inject the control signal in that specific node. So this problem might be unconstrained. So or it might be constrained. So your constraint might be for economical reason. So maybe you have a cost in adding a control signal to a node, or might be a hard constraint in which you simply cannot access that node. Okay.
Okay.
Yeah.
Questions at the moment? No?
Okay, so how do we model this? So we model this. So in the let's consider a standard graph. So here you have your network. You model this as an additional node. So this node, you call it pinner. This node has directional edges with respect to just a fraction of the nodes. And as Stefano was saying, so this direction, so you directly inject signals, for instance, in node 1 and 5, and then you want the topology of the network to make the work for you, to propagate the control signal for you in the entire network. So that's the basic idea. So mathematically, what changes in the equation that Stefano was showing yesterday? Well, you can put an additional term, which is which now we should recognize it as a proportional control action, because you have minus delta I, which is just 1 if the node is controlled and 0 if the node is not controlled, times the control gain Qi times the error, so the difference, the mismatch between the state of the pinner and the state of the node and the state of the pinner. And what are the dynamics of the pinner? Well, the pinner is just another node which is identical to the rest of the network. The only difference is that it's not affected by the other nodes. And so how do we define? So what is the reference trajectory? How do we set the reference trajectory? We set it by defining the initial conditions of the pinner. So it becomes a Cauchy problem. The solution is unique, and this is your reference trajectory, right? So now the question that arises is how many and actually which nodes I should pin to control the entire network. Okay, so should I control 1, 2, 3, 4? So, and which one should I control? So there is an interesting result which under quite mild condition on the vector field that describes the individual dynamics tells you that if the network is undirected and connected, you can pin any node in the network and then the graph will do the work for you. Okay? So then I have a question for you. So is it completely indifferent which node will pin? For sufficiently high control strength. So what do you think? So now we have a theorem. We have some theory that tells us, okay, so anywhere you put your control input, in the end, at steady state, you will converge onto the trajectory of the pinner, so onto your reference trajectory, so everybody is happy. So what do you think is going to be the difference if you pin one node or the other in the network? You cannot reply, yeah. Yeah. Yeah, the time needed to converge onto the trajectory. That's the answer. So if you are only worried about the steady state, then anyone is good. But then if you are interested in understanding what happens, then again you will need to look at the eigenvalue of some matrix. That's what you will need to do basically. Yeah, yeah. It's yeah, that's right. So it depends very much on the application, on what is the time that is acceptable for you, and then you need to understand if you need to study this second part of the problem or not. But now let's focus just on the steady state. So we say, okay, so we have the control input, the network is connected, it propagates everywhere in the network. What happens when the network is directed? So the network was undirected. Now the network is directed. I put some arrows in the network. Yeah.
In the previous slide, what is that quad? What is the origin of that?
Okay, so it's that assumption is so I'm considering the scalar case just for simplicity. So, that assumption in the scalar case becomes something like this. So basically, you are saying that the incremental ratio is bounded. So for the scalar case, this means just so if you divide that by x minus y squared, you find that the incremental ratio is bounded. So this is a clear is upper bounded, not lower bound, upper bound. So the idea is that this is also called one-sided Lipschitz because it's kind of Lipschitz just on one side. So that's the idea. So it's milder than Lipschitz. It might also be fulfilled by discontinuous functions. So that's the origin. And the term quad, it's for this quadratic thing. So it's common, especially in the not from the machines, but and it's particularly common the use of the word quad in the Chinese community, so in the Chinese literature. Probably in the Western, it's more common the use of one-sided Lipschitz. So, indirect interaction actually doesn't change much, as long as the network can make the work for you, so can propagate the signal everywhere in the network. So as long as the network is strong, the graph is strongly connected. Now, my question is, now what happens if the graph is not strongly connected? So, the original question is still, how many nodes there should be in? How do I, and which nodes should I pin? Yeah, 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 yes, exactly. So coming back to what we were saying yesterday, so often it's very useful to condense the graph into its strongly connected components, so you can get an idea from a much smaller graph. Now you can see this is a small graph still, but if you have a graph with millions of nodes, then you can do the condensation, and the condensation just has 4 nodes. So it can be a huge simplification in looking at it. So you condense it into the strongly connected components, then you get a much smaller graph. And now let me put some numbers so that you. And now which nodes of the condensation should I pin now, so that the signal can propagate everywhere? Two nodes. Which one?
Suggestions. If any one of you has studied classic graph theory, you may try to remember Kahn's theorem.
No, let's make it easier. So we just we just want the signal. We just we just want the signal. So we want to inject the signal in 2 nodes here. So we know that the answer is 2 nodes, so that the signal will propagate everywhere in the network. 1 and 4. 1 and 4. Yeah. So if now I control 1 and 4, then you can see that the signal will propagate in the entire network. What does it mean on the original graph? On the original graph, it means that I need to pin one node in this component, at least one node in this component, and at least one node in this component. Okay. Which one should I choose? Again, it affects the speed of convergence, not the convergence itself. Okay. Okay. All good for pinning control on the graph. So is it clear? The idea is, yeah, okay. Okay, unfortunately, as we know, sometimes we don't deal with. First of all, we don't deal with graphs, so we are not controlling graphs, but we are controlling hypergraphs. Yes. Yeah, please. F-
I know thousands of papers, okay, on pinning control,
Mhm.
which are based on Lyapunov response, changing the nature of the Lyapunov response. So your theorem says that if I have a strongly connected network and I choose any node, the asymptotic behavior, forget about time,
Yeah.
will be the one desired.
Yes.
So this means that asymptotically, the Lyapunov exponents are an average over infinite time. So I don't care about. So this means that in general, all these papers are wrong because they actually tell us to use multiple network pinning, not one.
No.
Difference probably that you're just controlling a fixed point here and they're controlling something else. I don't know.
No, I think. So no, no. What I think, I'm not sure about specifically to which paper. Yeah. He wants. He's asking to. So yeah.
Okay, sorry for this is a little bit technical question. I know a lot of this pinning control has a huge literature. If you go to pinning control, you find something like 2,000 papers. Okay, so and there are some of them which are based on Lyapunov exponents. That is, take my network, I take the conditional Lyapunov exponent. That is, I have a given solution that I want, and I measure the divergence rate with respect to this solution. And I use this as a criterion of deciding which pins I put. Okay. Now, the theorem that he just said that is independent on, if I understood correctly, independently on what I want to do, and if I can wait sufficient time, which is, I repeat, the case of a Lyapunov exponent, because Lyapunov exponents are in principle an average of an infinite time. It is sufficient for strongly connected network to pin a single node, no matter which one. This is the theorem. So I'm asking to him, who is a much more expert than me in control, what about these papers?
So I
Why
think
they say that it's better to do this or that based on the Lyapunov exponents?
So I think it's a matter of. I think probably I'm not sure about to which paper you are referring specifically, but if I have the right idea, this is because this theorem is based on the assumption of individual dynamics, which we just discussed. This one-sided Lipschitz. So under this one-sided Lipschitz, basically you fall back into the class two. The unbounded class 2 master stability function. And so that's why instead probably those papers refer to cases with class 3 or class 1. Yeah, that's the answer. Okay, so as you know, we need to now refer to what happens with hypergraphs. So because the network, it's so for two reasons. So one, you already know because we've been discussing yesterday. We don't need to repeat it again. So of course, the network itself. So the connection between peers, let's say, between the network that is being controlled, might be higher order. So you might have higher order interaction. But also, this is very much true in control, because when we are considering the standard pinning control, there is an underlying assumption that is never explicitly stated, because before hypergraph became popular, it was given sort of for granted. But the implicit assumption is that the node, the pinner, is able to individually measure the state of the nodes that he pinned, because he's able to then make this feedback action, which is proportional to the difference of the state. So he is able to measure, this, for instance, in this example, he's able to measure the state of node 1 and the state of node 2 individually. But this is not always the case in general, because in general, the controller might have an aggregated information on the state of groups of nodes. So I might have an idea of what is the state of a group of nodes in average, or in a convex combination, or in a general function. Okay, so for instance, one example is in systems biology, where the feedback mechanisms are always often based on cell fluorescence, but maybe you, for reasons of resolution, you may not be able to measure the fluorescence of a single cell. Okay, for instance. So what happens in this case? Well, first of all, you cannot model this as directed edges. So you need to consider that, for instance, you are getting an average measure of the state of node 1 and 2, and so your feedback control action will be a function of the difference between the state of the winner and the average state of nodes 1 and 2, which is what you are able to measure. So whenever you have sensing limitations, you will have a group interaction. So the control action will become a higher order interaction, so the control term. So it will be a function of the state of more than 2 nodes. And so you need to model this as an hyperedge, and in particular as a directed hyperedge. Now, what happens when you consider that? Well, what happens, we discussed it yesterday. So for the simple case of consensus, so even in the absence of control, we realize that when you consider a higher order interaction, there are things that happen that are that are quite different. For instance, when you go from a nearest neighbor on a graph to a nearest neighbor of an directed hypergraph, you will have divergence. Okay, but now what type of formalism do we choose now? So yesterday we used target hypergraphs, so we were focused on the node that was receiving the signal. Now we would like also to focus on the node that is sending the signal. So we will be using a different formalism now, because now we want to know who is influencing and who is influenced, right? And so the formalism that we will use, there have been different formalisms proposed. For instance, there was this this formalism of one-directed hypergraphs from Gallo, Muolo, Frasca, and others. But the one that was most suitable for our for the purpose of generalizing pinning control, to consider the limitation on sensing, was to consider to model hyperedges, directed hyperedges, as a set of nodes which is sending the signals, which become the tail of the hyperedge, and the nodes who receives that are the heads. So think of this. So you, in a standard directed edge, so you have a tail and a head. So how do you generalize this to when you want to consider a hyperedge? You generalize it as an object which has multiple tails, and the tails will be the nodes that are sending the signal, and multiple heads which will be receiving the signal. And what well, tail, well, it's just tail and head of an arrow. That's the tail and head of the arrow. That's not, yeah, that's the where this comes from. Yeah. Yeah, yeah, but it comes from the arrow. So the arrow of the edge. That's the thing. So that's the idea. So the tails of this generalized arrow sends a signal to the heads, and the signal itself is a function of the states of all the nodes involved in this interaction. So they receive, they send, and the signal that is received and sent is a function of the state of all these nodes. Okay, so that's the formalism that we will be using. Okay, so basically it's defined as two subsets of. So the hyperedge in this case is defined as a pair of subsets of V. Okay. Now, well, so what is a, well, first observation. So in the standard pinning control, so instead of considering, so since the pinner basically is just another node in the network, right? So the only peculiarity of this node is that it has unidirectional links with the rest of the network. So we can also rewrite the equation incorporating the control action into the coupling term, right? So we can put it inside the coupling term and consider the pinner just as the nth node of the network, which is not affected by the other nodes, simply just as simple as that, right? So we can do that. We can do this also when we generalize this to to hypergraphs. And so what we need to point out is that what is changed here is the coupling function G, well, which will be, instead of a function of the state difference that we have here, well, here we have the output difference, but yeah. So it's a function of a convex combination of the state, of the difference between a convex combination of the state of the tails and a convex combination of the state of the heads. Okay, so this, importantly, this is an instance of a synchronization non-invasive protocol, because this is going to be 0 when the nodes are synchronized. Okay, so this is this is important to point out, and this allows us to incorporate in this term also the pinner, because now the pinner will be a node which will belong to hyperedges, of which it will be the sole tail. So the hyperedge so if this is the pinner, and you have 3, and he's pinning these 3 nodes, 1, 4, and 7, for instance, and measuring the aggregated state of these 3 nodes. So you will have this control action will be described by a directed hyperedge with just one tail, which is the pinner, and 3 heads. So for instance, this could be the corresponding coupling term could be a function G of the difference between the state of the pinner and, I don't know, the average or any convex combination of the states of the pinnet nodes. Okay, and so this is exactly what is pointed out here in these slides. Okay, so we generalize this diffusive-like interaction here to this sort of generalized diffusion in which you consider the difference between convex combination of the state of the tail and convex combination of the state of the heads. Okay, so now how do we study that? Okay, so first of all, can we adapt the tools that have been used for networks also to deal with such cases? And what is the impact that higher order interaction have on our ability to affect the control of the system, to affect the behavior of the system? So can we quantify that? Can we understand that? So to understand that, there was one interesting association that we could do between the topology of a directed hypergraph, defined as heads and tails, with hyperedges defined as heads and tails, as I explained, and a special class of sign graphs. And this comes from one observation, from two observations if you want. So the first one is that the argument of the function g can actually be written like this. So where basically you have positive, can be looked at as some positive edges here and some negative edges here. Okay, so that's the first thing that you can notice. But of course, this is still a higher order interaction, because then you have a nonlinear function g here. So in principle, you still cannot use this association. But when you linearize around the synchronization manifold, which in this case is a specific solution, so it's the one of the pinner, then what happens here is that it appears a matrix Lij. And this matrix Lij, we call it L, but that reminds us the Laplacian. But in common with the Laplacian, but it's not the Laplacian of a standard graph with the property that we have seen. That is the Laplacian of a sign graph. So it will be zero row sum, but its diagonal elements, or of diagonal elements, can be positive or negative. We don't know. We are not guaranteed about the sign. Okay. So this changes something, because yesterday we have seen that the Laplacian is has the eigenvalue 0 with associated eigenvector 1, and this is still true because the matrix is zero row sum. But the other properties of the Laplacian gave us the information that its spectrum was all contained in the right half plane of the right half complex plane. Unfortunately, now this is not anymore true. So the Laplacian does not have necessary eigenvalues with positive real part or zero eigenvalues, but may even have negative eigenvalues. Okay? Which can be a problem for stability. Okay, so let's look at this association. So this association is interesting because it's quite simple. So you can build it in an instant. You can build this association, because it basically, to go from the directed hypergraph to the associated sign graph, the association, let's say, is exact only when you linearize. So when you are far away from the synchronization manifold, of course, this association does not hold anymore. But when you are around the synchronization manifold, you can do this association, and you can replace an hyperedge, directed hyperedge, with positive edges from each tail to each head, and negative edges between the heads. So that's what. So you are getting this sort of repulsive interactions between the heads, and you have these attractive interactions between heads and tails. Okay, and so once you do that, then you can use all the tools that you have been using for networks on graphs. Of course, with the caveat that now you are considering that the Laplacian may also have negative eigenvalues, and you need to account for that. So you can use Lyapunov methods that we haven't mentioned, but that we had just mentioned. We will not go into the details. And also you can use the mass stability function approach that was introduced by Stefano yesterday to study convergence. Of course, what happens is that you will have to study, since the Laplacian is now can have also negative eigenvalue, you need to study the Lyapunov, the mass stability function in the entire complex plane, not only in the right half of the complex plane. Also, this explains something that we were observing yesterday, because the fact that the Laplacian may have negative eigenvalues, when you are in the consensus case, This implies that the dynamics, the matrix, the dynamical matrix will have some we might have some positive eigenvalues, and so you can have instability. So this is what was happening yesterday in the consensus case. So if you model it with tails and edges, you will see that the associated Laplacian will have also some one negative eigenvalue, which will be associated, since the dynamics is minus sigma L, will be associated to an unstable mode. Okay, so, well, we can use the mass stability function. The only thing that we need to consider is what was being discussed at the very end of the lecture yesterday. So when you build your sign graph, of course, the Laplacian that you will obtain in general will be not symmetric. So you are not guaranteed that the Laplacian is diagonalizable. The Laplacian may not be diagonalizable. But any matrix can be, luckily, any matrix can be put in Jordan block diagonal form. Okay, so you take any matrix, there will always exist some transformation, some invertible V, such that you can write the Laplacian as Vj, V the inverse of V, where J is a block diagonal matrix. And the ith block of this matrix will have on the diagonal the eigenvalue, the ith eigenvalue, and on the lower diagonal a vector of ones. Okay, so when you study the dynamics associated to this block, so to that specific eigenvalue, when you do the linearization around the synchronization manifold and you transform, you apply the transformation, so you put in these new coordinates so that you put the system, you block diagonalize the Laplacian, what you will get, the ith block will have this shape here. So, well, the first block will be exactly the same as the one that was discussed by Stefano yesterday. So when the mass stability function is negative for the corresponding lambda I, this term will converge exponentially to 0. And then, so eta 1 will converge exponentially to 0. And so this will be, you can look at this term here in the second equation as an asymptotically vanishing term. So you just need to wait that it vanishes, and then you will get again the same equation here. And so also eta I plus 1 will go to 0. And so on up to eta I plus b minus 1, where b is the size of the Jordan block. Okay, so in the end, nothing changes in terms of the condition to get stability. So you still have to look at you can still introduce the master equation, and then you evaluate it at the eigenvalue of the system. If it's negative for all the eigenvalues of the system, which might be, in this case, positive, complex, it can be real and complex, and the real part can be positive and even negative this time. So if it's negative for all values of the for all the eigenvalues of this the Laplacian associated to the sign graph, then you will have convergence onto the Binder trajectory. Okay, so we have extended the use of the mass stability function also to the case of directed higher order interaction. Okay, so what were the tricks? Well, the fundamental trick was this association with the sign graph, so that we could go back to matrices again. So with not tensors but matrices, and so we could work with it. Now, let me see how. Okay. 20 minutes. That's more than enough. So now let me show you one example. So the answer to the first question is yes, we can use the tools. So with some smart association, then we can use the tools from that we had for networks of pairwise interactions. We need to be just careful with what we do. And now, what is the effect of higher order interaction on our ability to control? So the fact that we have this lack of resolution in the measurement, how does it affect our ability to control the network? Okay, so let me show you this experiment. It's somehow you will see a somehow counterintuitive result, but actually it can be, of course, it can be explained as a reasonable explanation. So let's take 100 Rosler systems coupled on an Erdős-Rényi hypergraph. Erdős-Rényi hypergraph, I mean that the degree distribution of all the orders follow a Poisson distribution. So the pinner will set, of course, the synchronous solution, and then we introduce this parameter R, which basically modulates the resolution of the measurement. What do we mean as the resolution? So basically, if this R is equal to 1, we mean that the pinner, we are in the case of the classical pinning control. So the pinner is able to measure individually the state of every node. Okay. If instead we in the case R equal, the opposite is the case R equal to 0.01. In that case, just gets an aggregated measurement of the entire network. So it just measures the average state of the 100 nodes. Okay. And then we vary this parameter R between these two extremes, so the resolution is increased from just being able to have one aggregated measurement to being able to individually measure each node. And then we compared the control performance for the different resolution in terms of the maximum value of the master stability function evaluated at the eigenvalue of the Laplacian. Of course, we are considering the enlarged network, which includes the pinner when we are doing this. So what we get is this. So of course, you have just one point when in correspondence to 0.01 and 1, while in the intermediate resolution you have several options because you can measure, I don't know, 50 nodes. Now, how do you choose these 50 nodes? So there are several random selections of the 50 nodes of which you measure the state. So when you increase the resolution, well, the first part is makes sense, right? Because you increase the resolution of the control action and you are decreasing lambda max. You have instability at the beginning, then you start to have stability most of the cases, then you always have stability, but then at some point things get worse. And with the highest possible resolution, so when you are able to measure every node, you get the worst result. You get instability again, and you get the worst result. So why do we see this? We see this because when we have the maximum resolution, basically we are pinning every node, individually sending a control action to all the nodes. So what we are doing actually, so we are modifying, we are just shifting all the eigenvalue all together to the left. But the thing is, or to the right, well, but the thing is that we are in a case of a type 3 master stability function. So we are not modifying the shape. So we are not modifying the compactness of the spectrum. So we are making, and so basically with this individualized control action, yes, we are changing the eigenvalues, but we are not changing the ratio between the largest and the smallest. And so we are not actually doing something. So if we were in a case in a type 2, then of course having the best resolution would yield the best results. But for type 3, it's not so trivial. Okay, so you need to be careful. Yeah, yeah. And of course, this phenomenon, what happens is, what happens for intermediate resolutions? The spectrum is deformed, and it plays actually in your favor, and the ratio between lambda n and lambda 1 is reduced. This happens not always, but happens when the network has directed when the network of the followers, if you consider only the plus edges in the sign graph, as a directed spanning tree. So you get some information. So you also get the topological information from this. So actually the network needs to have a directed spanning tree. So but this becomes a necessary condition now for control. So it's not anymore as sufficient. So your condition, which was sufficient earlier, becomes a necessary condition and is applied to the plus to the positive edges, to the graph composed by the positive edges of the sign graph that you have obtained. And so you obtain a topological condition, but which is just necessary. And interestingly, you need to let's say you need to be careful of what you wish for. So when you increase the resolution, it's not always, this is not always good for control. But as all the the non-pin, the non-pinner, the rest of the net. I have a question, I have a last question for you, because you always need to be aware of counterintuitive statements. So, can it be that it's not good to be able to measure every node? So what can I do to make it work better? So the thing that is happening is that I have a control gain k equal for all the nodes, and I multiply it for the error. And so what is happening is that I'm just shifting the eigenvalues of the Laplacian. Now, what about if I want to deform the spectrum? What should I do? So if I take a matrix and I subtract from this matrix a matrix which is proportional to the identity, then I will just shift the eigenvalues. But I have the identity matrix just because the coupling gain is identical for all nodes. If I consider the coupling gain different, so if I tailor the coupling gain suitably for every node, then I can overcome this issue. So instead of having a diagonal matrix, I have a diagonal matrix instead of a multiple of the identity. I can modulate the entries, and so I can I have more degrees of freedom, and I can shift. Yeah, that's right. That's right. So if I have the freedom of choosing a different coupling gain for every node, then I can fully exploit the advantage of the resolution. If I don't have this freedom, then having a high resolution might be a problem instead. So that's if you want the trick here. Okay, so concluding, well, so again, the take-home message is that, sometimes, first of all, again, the formalism that you use to model directed interactions. So both of my talks have been discussing directed interactions. So the formalism that you choose depends very much on what is your scope. So yesterday we were focused on the node receiving the signal, and we needed, in particular, to provide some balance condition to guarantee average consensus, right? And so we needed to a formalism for which it was easy to guarantee such a balance. And such a balance was guaranteed by this circulating property in the graph. Now we don't need that. We don't want a balance. We want everybody to go to the Pinner trajectory. So now the thing that we needed is to identify the nodes that were sending the signal and the nodes receiving the signal. And also, we crucially, the trick is that we use is, first of all, we focus on synchronization non-invasive protocols. And in particular, we consider a protocol in which, when you linearize the dynamics, a protocol which makes sense from the point of view of the application that we are considering, because if you have a nice protocol which simplifies the computation but doesn't make sense for your purpose, then it's useless, right? But for our control action, this is precisely what we were looking for. And when you do that, and when you linearize the dynamics around the synchronization manifold, you get back to matrices. And so you can resort to all of the tools that you can use for pairwise interaction, with the caveat that you are now considering also negative interactions. Okay, so what are let's say the open problems here? Well, some were already mentioned by Stefano yesterday. So, well, of course, the nodes that you consider might be non-identical. So you might have nodes with different dynamics. This is something that has been dealt with in the case of pairwise interactions, but is being also studied now for higher order interactions. So what happens? And in particular, and then what happens when the interactions are non-diffusive like, and in particular non-synchronization non-invasive? So what happens in such cases? So this is very, very critical. And then one last question, which I find, for which there are results from, in particular in the fields of neuroscience and using tools from information theory, is how do we detect higher order interaction from data? So now we are talking about models, but what about when we have time series? So we have a sequence of time series from the nodes. So we have several nodes, several systems. We measure the time series, and we would like to understand. So are these nodes interacting in a pairwise fashion or in a multi-body higher order fashion? So that's an interesting question. There are results on this, but this is still open. And in particular, can you detect if this interaction is directed? There are some tricky questions here. Okay, this is a list of references on what we have been discussed here. So there is a nice book that I can introduce on feedback systems. Of course, there are tons of books, but this is a nice one to begin with. And then some works on pinning controllers on digraphs, and specifically all the formalism. Well, here I had to refer to some of my work here because this formalism on directed library graphs is contained in this paper that you can see here. You can have a look at these physical review letters, for instance. I think it's a nice reading particularly for those of you that have background in physics, which is the vast majority. And well, finally, some acknowledgement. One of them is in the audience, is Roberto, and the others are colleagues from Napoli and Benevento, Milano. Francesco Lo Iudice, Fabio Della Rossa, Davide Liuzza, and Roberto Rizzarello is here. Thank you.
Very, very good. So we have about like 10-15 minutes worth of questions. I'm pretty sure there are many questions because the talk was very good. This microphone doesn't work. That's better microphone.
So I have a question that more than a question. I thank you for the beautiful, really beautiful presentation.
Thank you.
Just a caveat for the students. What you have described is the control of synchronized states of the network.
Right.
Which is a specific state of the network. That is, state where all the nodes repeat the same dynamics. That's why you have one unique pinning control, which then input these dynamics to the rest. It's a very interesting problem, but I would put as open challenge, even before the ones you put, since I have some ideas I want to discuss with you later on, the idea of controlling a generic state of the network. Generic state of the network means not necessarily synchronized. I may be interested that node 1 does something while node 2 does something else, while node 3 does something else. But each one of these three nodes is doing what I want. No? So this is not a synchronized state.
That's right.
And I think I have a way to suggest to you, and maybe we can expand your treatment to this because it's very similar. It uses also the master stability function. It's just a way of not having a unique pinning, but having a master-slave network,
Cool.
a master copy of the
Yeah.
network, and then
Links from
directed
the
pinning
master
from each node of the master to each node of the slave. But you can use exactly the same formulas, I think. And this could be a very nice extension of what you work, because then if you want to control synchronization, you can fuse the master into a single node. But if you just want to repeat the master on whatever possible state of the master, which is a copy of the slave, this is a different question. So the idea, you know, it's just you observe your system for a while, you make a movie, then you return a day after and you want the system to repeat the same movie that you recorded the day before. This is a sort of control that can be done.
Yeah, of course you can.
And we can discuss this. But this I
With
would
pleasure.
put as an open challenge.
Yeah,
because
yeah.
it's still to be done.
Yeah, definitely. Yeah, of course, this is just control of synchronization. Then control is it's a wider topic, and so depending on the goal that you have, you can design different strategies.
Next question from here.
A very nice lecture.
Thank you.
I have a question. One thing that caught my attention was how a higher resolution is not always beneficial. And this reminded me of some results in other fields, for example, in biology, ecology, finance, for example, investment strategies and so forth, where there are situations where more information doesn't actually help. So I just wanted to understand, in this particular case, the higher resolution is only not beneficial if all the couplings are the same.
That's right.
But if you have freedom over the couplings, then
Then you
more
ca-
resolution is always beneficial.
Yes. Yes, you are correct. Yes, you are correct. So it depends very much on if you are constrained or not on the coupling string. If you can design it individually for every node differently, then you can exploit this additional resolution and work it in your favor. Otherwise, it can work against you. That's
Next question.
I have a very limited knowledge on control systems, and when I did my undergraduate course on it, we always use like set points. So like in PID controller, you pass the set point there, and you control where you want it to go. And this may be related to what Professor Boccaletti said regarding not synchronized networks. Because here I didn't understand exactly what was the set point, what kind of variable you were trying to control in the network. Was it only the synchronization, like to achieve synchronization between nodes, or the variable?
So at the beginning we talk about stabilization and tracking. Basically here we are tracking a trajectory. But the trajectory is the one set by the pinner. So you have the solution of so you have the pinner dynamics and its initial condition. You have this unique solution. That solution will be the reference that you want all the system to follow. The type of so since you attended the course, an undergraduate course in control, so the type of controller that you are using is proportional, but of course you can use more refined strategies that have been proposed in the literature. I haven't mentioned them, but you can also add an integral control action, a derivative control action. So you can have you can have an additional protocol which considers also the integral of the error, the derivative of the error, and so you can enhance performance.
So, but continue what Professor Boccaletti said. So I understand. You're controlling where the whole network is going to converge, not only a single node.
All the nodes converging onto the same trajectory, and the trajectory is the one defined by the pinner. Of course, you might have different goals. But if we are controlling synchronization, this is what we want to do. What you want to do.
Okay, now it makes more sense.
A difference for what you were seeing yesterday. Yesterday we were showing whether synchronization emerged spontaneously or not. Now we are enforcing it, and we are enforcing it on a special solution, not on a general solution.
Thanks.
Okay, any more questions? sure. I mean, talk was very good. So there you go.
My question is about the node that you choose to input the control, the pin. You said that the difference when you choose the node is how many time you have to converge the nodes, right? And my question is, you always look for the hubs in the network because you always want to the time to converge faster, or this is not always the case? Like you sometimes doesn't want to the convergency to be like the faster you can be, or is it like all the time?
Okay, so the truth is that there is not a general answer to this question, in the sense that what you should do, you should look at this lambda max, you should make it as negative as possible. The more negative it is, the faster you will go to synchronization. So in the end, you will have to look at the eigenvalue. So you need to check, I pin this node, then I look at the effect on the eigenvalues of the Laplacian, and I see how I move the eigenvalues, and those will tell me how quickly I will go to the I will converge to the synchronous state. How is this related to the structure, to some topological properties? Well, there have been studies that tested some different centrality measures, among which the degree, and so there are numerical evidence, and in a certain type of networks, pinning the hubs is better, or but then of course it depends very much on the type of system that you are studying. So you have to consider the dynamics part, because of course this will affect the type of master stability function. So there is not a unique answer for any network. It depends on the class also of the master stability function.
Okay, thank you.
In general, making a general statement, and general statements are always wrong by definition, there is a correlation between the time scale at which you converge and the degree of the node. So what you said is better to put in a hub that, but it's a very mild correlation, and there are very clear counterexamples. You can make some counterexamples. For example, you take, I don't know, a network made of two communities, two hubs with 1 million nodes, but they are not connected among them. And there is a third node in the middle with only two connections, one to the right, one to the left. So this node, which is very low degree because it's only two, and the other one has millions, has the same control importance as the other two. Because if you control this, then the control goes directly to the two hubs. Whereas if you control the hub, you are very much facilitating in the nodes which are connected to the hub, but then it takes more time to go because the flow has to pass through this central node. So there is not, as you said, a unique recipe.
Yeah.
It depends very much on many things. Between the centrality is another one.
Yeah.
But you can use also,
Yeah.
Anyway, we have time for one last question.
So do forgive the ignorance. I don't know much about control theory. I was just curious about something. Okay, you said about pinning nodes, controlling node states. Is there something, or do you know of, people have studied, controlling instead of node states, controlling edges, maybe the coupling between nodes? Is that something that...
Controlling edges, well, you can, there are several instances, there are several ways, depends on what you mean by controlling edges. So so because there have been works that have controlled, adapted the coupling strength of the between the nodes from, so they can be different from edge to edge and can be modulated based on the error or the mismatch between the endpoints on the, so this is one way of controlling the edge in the sense that you are controlling the weights of the edges. Another type of study is controlling the edges in the sense of removing and adding edges in order to enhance the controllability. So you, of course, in that case, you need to frame your problem properly. So what are your degrees of freedom? How much does it cost to add an edge? How much does it cost to make a move, to make a variation to the structure? So it depends on the problem, depends on also of what you think, so on what you can do actually. So is the network already there and you need to control and you cannot change it, or can you act on the topology? Or are you designing the network from the beginning? So in that case, you might choose a structure rather instead of another. So there have been, for what I've seen, there have been both works that decides which edges to add or remove to the network and how to design the network topology, and other works that have been working with the existing structure and modulated the gains, so modulating the coupling strength, so the weights of the edges. Roughly speaking, this is.
Thank you.
Yeah.
Okay, so before concluding the session, because we are kind of like precisely out of time, I'd like to mention that afterwards we're going to make it really international institute talk. So we're going to have a talk from Ludovico Minati, who is literally on the other side of the world. In fact, 11 hours of difference from here. So for 1 hour is not like precisely on the other side of the world. And obviously it's going to be online. So now there's a coffee break. But before that, I'd like you all to thank again Piero for the wonderful talk.